So I'm going to prove here theorem 97, and I'm going to rely heavily on lemma 95, as you might expect, because it's a lemma. A lemma is a theorem that is used to prove another theorem. So theorem 96 says you have a set B with n elements. Maybe I'll give it a name. And all the following are true. And how about I'll let y be y1 to ym be linearly independent. Then 1. No linearly independent set of V contains more than n elements. Well, in other words, so this is a generic linearly independent set, and oftentimes we'll denote the number of things in Y by that. So M is equal to that. That's going to be less than or equal to by lemma 95 if Y is a finite linearly independent set, and here Y is finite, has M things, and is linearly independent, then there are at most as many elements in here as any sort of spanning set. But a basis is a spanning set, so we're going to let x equal b, and there are n things in there. So the number of things in Y has to be less than or equal to n, which is exactly what we're trying to prove. So if it's linearly independent, you can't contain more. That means you have to contain less than or equal to. So we're done with that. 2. Every linearly independent set of V with n elements is a basis. This comes from the proof of lemma 95. Recall that we had z, maybe I'll call it z naught, we could let it equal to b. I let b equal to x in the other one. And I had this process where I let z1 be z naught, in other words b, minus some basis element, but then I'm going to go throw in y sub 1. And I can continue on. Z sub L is going to equal Z sub L minus 1 minus some sort of a basis element, union Y sub L. And so this is part of the proof of theorem 95 is I had the set. And the key thing is all of these continue to span. These all span V. So I start off with something that spans V, and by doing this process of replacing one of the B's with a Y, it still spans. That's the point of the proof of this, and that's why it works. So each time I replace a B and then replace it with a Y, which means after the nth step, I'm going to have K Y sub n, which means I've added all n elements of Y in here. Y1 is in the first step, Y2 in the second, YL in the nth step, Yn in the nth step. But I've also removed one element of B each time. Since there are only n elements of B, I have that B is all gone. So I've put all the Y's in there, I've taken all the B's out, so that means that Y is equal to this. In particular, Y is going to span. That's the proof of lemma 95, says that the Cn also spans V. So it spans V. Y is linearly independent by assumption. So Y is a basis. Why is it a basis? Because it's linearly independent, and the proof of lemma 95 says that all these things span. So we're done with that. If you have n elements, then you're replacing exactly one B with one Y for every single B, and so you're going to eventually completely replace the B's with Y's, and so your basis. Step 3, every linearly independent set of Y contains a basis. So we're back to assuming that there are M things in there, or is contained in the basis, sorry. And the way we're going to go about this is step 1. How about let's Y naught equal Y. And then step 1 is going to be if B1 belongs to the span of Y, then Y1 is going to equal Y naught. Otherwise, y1 is going to equal y naught, together with me throwing in b1. And similarly, I can continue this way. Step L is if b sub L belongs to the span of yl minus 1, y sub L equals y sub L minus 1. I don't do anything. Otherwise, y sub L equals y sub L minus 1 together with b sub L. And now I'm going to consider y sub n. So, in other words, I'm going to go through each basis element. If the basis element is in the span of what I already have, then I'm going to ignore it. Otherwise, I'm going to throw it in there because I think it might be useful. And the key thing is each of these is going to, well, yn is going to span the entire thing. Yn spans b, since all b sub I belong to yn. So b belongs to yn. Why is that? Well, at each step something happens. At step 1, I'm testing to see whether b1 is in there. If it's already in the span, then I know it's in that's going to be in the span of y naught. That should be in the span of that. So I can get b1 from what I already have. Similar with bl. or if b1 is not in there, then I throw it in there. I make it in there. So it's definitely going to be in the span. Same thing, bl is either already in the span, which means I can get it as a linear combination of what I already have, which means I can get it in particular, or I'm going to throw it in there. So every basis element is in the span of y sub n, which means I can make any basis element I want, and then take linear combinations of those basis elements. So since the basis element's in the span, that means that yn spans v. So I need to show that it's linearly independent, though. Because if I can show it's linearly independent, then yn is the basis. If yn is the basis, it contains y, because I never throw anything out from y. So the way to show it's linearly independent is I'm going to show that each yl is linearly independent. Why is that? Because maybe I'll just work my way up. Y naught is linearly independent. Y1 is, since either y1 equals y naught, which is linearly independent, or y1 equals y naught union b1. Now, it could be that throwing the b1 in there screws it up. It could be that c1 y1 plus that plus cm ym plus how about d b1 is equal to 0 for some non-zero coefficients. But if that were the case, either d is equal to 0. But if d is equal to 0, then I have all these things equaling 0, which means that these aren't linearly independent. So d cannot be 0, which means I can make b1 is equal to d inverse c1. What do I want to do? Negative d inverse c1 y1 plus plus negative d inverse cm ym, which means that b1 is in the span of the y's. But I picked b to not be in the span. If b1 were in the span, I didn't include it. So by this reasoning, same reasoning, whenever you start with a linearly independent set and you throw things in only if they're not already in the span, that's going to keep things linearly independent. All yl are li. So yn is linearly independent. So yn is a basis. Not only any basis, it contains y. all I did is I started with y, and then I threw some stuff in there. I threw basis elements in when I needed. I didn't throw them in when it would cause a nonlinear independent set. And notice, by the way, I didn't need to work with the basis elements here. I could have worked with anything. So. But anyway, that's where we are. So we're done.